Okay, so we're going to wrap up this example here. We're talking about south 70 degrees of west. When we look at our finished diagram here, what we're saying is with the starting direction, so we have our south value, right? Means we start down here, and then I go to the west 70 degrees. And so my south 70 degrees west is interpreted like this. I'd have if I was in my graphing, I'd be in the third quadrant going in that direction. Alright, so we have two types of bearings that we can talk about. One is what we just talked about, which is a quadrant bearing, which is the idea here of a south 35 degrees east. So I go south 35 degrees to the east, and that would be my quadrant bearing. A true bearing is always from north at 0 degrees. So for a true bearing, it's a little bit different in that I have my north, west, south, and east. And what we say is this is 0 degrees. We're always going in a clockwise direction. So a true bearing of 145 degrees, a true bearing of 25 degrees, the way that they have it up here, would be from the north, I would go down 25 degrees. So that distance there of 25 degrees. And so that's a little bit different. Usually for our trig, our standard position would be here at 0, and we go counterclockwise. A true bearing north is 0 degrees, and we go in the clockwise direction. So you just need to kind of keep in mind which type of measurement it's giving you, and then interpret the vector from there. Alright, so another couple of examples. We have a bearing of 0, 30 degrees. So again, this is a true bearing. We start with north at 0, and then we just go 30 degrees in the clockwise direction, and that would be my vector. I have something at 140 degrees, again, from the horizontal. So from the horizontal is our standard position, where 0 is over here, and I go 140 degrees in the counterclockwise direction because it's from a horizontal position. And then this is my quadrant, right, where I have south 60 degree west. So I start in the south, and then I go 60 degrees towards the west. And then the magnitude of my vector, the 30 miles per hour, is what's going to go here. Now, you see they've scaled it, right? So this would be actually drawn to scale, where I'd have 20 miles per hour is 1 inch. So if I was to take 30 and figure out how many inch measurements that is, well, 30 divided by 20 is 1.5 inches. And so this to scale would be 1.5 inches. One thing to keep in mind is that vectors are proportional. So if we have a vector that is like this, let's say that that's 20 miles per hour, right? If I wanted a vector that was half as big, so I had 10 miles per hour in the same direction, it would be half as long, right? If I wanted something that was twice the speed, it would be twice as long. So we can use vectors, just even looking at them, to kind of get a sense of what's a larger or a smaller quantity in terms of the magnitude as we're drawing these out. So here's another one. Again, we have a bearing, so this is going to be a true bearing at 0, 25 degrees. A true bearing, again, starts at north being 0. We could use a protractor and a scale to get that, but there's our value, right? This is really what we're interested in. Do you have the vector set up in the correct part, right? So you have those values down there, where you have your 25 degrees, going from north, and then you had go clockwise because it is a excuse me, because it's a bearing. Alright, so here's one for you to do. You're going to draw this vector. It's giving you a magnitude and it's giving you a direction. You need to figure out which type of direction. So is it a quadrant bearing, a true bearing, or is it from a horizontal? And then sketch that on your paper. Alright, one thing that we want to think about is how do we actually combine vectors. So how do we take two vectors and get what's called a resultant of those vectors? So one thing we want to think about is just kind of what's happening here. If I have two people, let's say that I am pushing a box, and I have a person that's pushing that way, and I have another person who's pushing that way. We all kind of get an intuitive sense, if we're pushing on a box like that, that we'd have the box is going to go up in that direction. Okay, it's not going to go backwards. It's not going to move around. It's going to, if we're both pushing in this direction, it's going to kind of go up in that direction. So the key idea with adding vectors is, what we would do is we have to think about, if one person pushes it and then the other person pushes it, where would we be? And the way that that looks geometrically is to take our vectors and we get what's called a resultant vector. And so let's see if I can do this here. If I take my vectors, I'd have the black one is going there, and then the red one is going there, and then the resultant vector is that. Okay, so again, that's kind of what we sketched out here. The key idea with this, and that's what they have down here in their diagrams, is that you add vectors head to tail. So the end of this point, or the head where the vector is pointing, has to line up with the tail of the next one, or the initial point. Right? What we can't do is add them tail to tail. So if we did that on the above example, right, if I put the black and the red vectors together tail to tail, I would have something that looked like this. I'd have the black like that, and then I'd have the red tail to tail like that, and then my resultant vector would be weird. It'd be going the wrong way. It'd be going over there. That's not what it looks like. Again, if you have a box that you're pushing on in these directions, it's not going to go backwards. Doesn't make any sense. So again, you keep them together with head to tail. Another way to do it, it's really kind of the same way, is to draw a parallelogram. So basically you do the diagram that I had up here, right? But you don't have your values, you don't connect them that way. What you would then do is you need to basically double them up and draw a parallelogram. So like that, and across, and then your resultant vector is again the right direction. So either way, whatever you prefer, whether you do it with a parallelogram, so in case like this, and then draw a resultant, or if you just go head to tail, then you just need to make sure that you're not doing something where you have tail to tail without the parallelogram. And again, if you take a step back from it and think about things being pushed around, it should kind of make some intuitive sense as to how these would add together. Alright, so we have some values here that we're going to look at. So we want to basically make sure that we sketch these correctly, that we have the sketch correct, and then from there we can determine the resultant vector, because we really have two vectors here that we are interpreting. Okay, so we're going to just sketch out kind of the idea of this today, and then when we come back for the second part of this section, we'll actually solve this algebraically and geometrically. But we want to get an idea of kind of what we're talking about today. So for this one, we want to make sure that we have, we'll set up our coordinates. Oops. So I'm going to draw as best I can my axes, and then this is north, and then I have Shelly walking 2 kilometers north, 30 degrees west. So if I start in the north and I go 30 degrees west, I'm going to be over here this way. So I'm going to sketch that out like that, and that angle is 30 degrees, and she's walking 2 kilometers, so it's a 2. Now what I need to think about is I have 2 kilometers directly east, and so directly east, one way to kind of interpret this is if I had another set of axes that were right here, right north at the top, if I'm going directly east for 2 kilometers, that is going to be in this direction over here. And so that's 2 kilometers. So my resultant, because I've gone head to tail, the resultant vector is going to be here. So I'm going to have to do some math. We're not going to do it right now to figure out our values here, but basically we're going to implement the law of sines or law of cosines and some right triangle trig to basically abstract out. We have created a triangle that looks like this, where I have a 2 and a 2, and then I have part of an angle in here of 30 degrees. And so we'll be able to kind of figure out, using some of our geometry skills, how to solve that down the road. So the book walks through the different interpretations of that, but that's, if you understand the setup and kind of where the complexity lies, that's good enough for right now. All right, so that's what they do. They go through it, they use a scale, and what they can show here is that they have their vector where we had it, and they have their 2 centimeters east right there. You pick it up just like we had it, and we end up in that first quadrant somewhere as we're going about it. Then they go their triangle method, and then they show their parallelogram method. Alright, one thing we can do is take a vector and multiply by what's a scalar value, so we can scale it up or scale it down. And so if I have a vector, if this is vector A, and I want a vector that is 2A, right, basically we can take this vector here and double it, and that's going to be 2A. So we can scale it up by multiplying, and that works kind of the way you think it does. It doesn't change the direction, it just makes it longer or shorter. You're just affecting the magnitude as you move forward with it. So we can also scale by a negative value, right? A negative value is going to flip a vector around. So if I was looking for A minus 3B, right, minus 3B, if B, let's see if I can draw on top of that. If B is that direction, negative B is going to be in the other direction. And if I take 3 of these and put them somewhere, there's 1, there's 2, there's 3. If I'm looking for A minus 3B, I somehow need to take vector A. So I'll try to draw on top of that one. There's vector A. Okay, to put those together, again, I have to go head to tail. So I'm going to move, I'm going to move vector A, so I have some space, and then we're going to take our 3 B's and go head to tail. There we go. And then my resultant vector, the thing that's my end result, is again going to be from my start to my end, and that is going to be A minus 3B. And that's it. So again, you can use these geometrically. Again, your sketches just need to be in the right ballpark as you're going forward with them. And that's what they just show. Alright, so they use their triangle method. That's fine. We're going to use either that head to tail or the parallelogram method. Alright, and then there's my resultant. Alright, so you're going to, on your handout, we have a vector n and 2m. You need to write the resultant of I take n and twice m and add them together. Again, making sure that you go head to tail.